Welcome to the Deep Dive, where we take those dense research papers, those technical docs, and we really try to wrestle them down into clear, crucial insights for you.
Hmm.
And today, we are deep diving into a shift that moves way beyond just, simple coding tools. We're talking about the age of the autonomous AI engineer.
It's a huge difference. I mean, it's the difference between an AI that just finishes your sentence for you, like code completion, and one that can actually conceptualize, plan, architect, and then ship a fully functional software project all on its own.
And the ultimate stress test for that kind of capability is what this research calls high-fidelity document-to-code-based synthesis.
Which is a mouthful.
It's a huge mouthful.
Yeah.
But what it means is taking an incredibly complex, unstructured, and frankly often confusing specification, like a huge scientific paper,
With all the pros, the equations, diagrams,
Oh,
pseudocode.
right, all of that, and synthesizing a complete executable production-grade code repository from just that one input. That's the mission today.
And the framework we're going to be analyzing, it's called DeepCode. And its central claim is that it has cracked the fundamental conflict that has crippled these autonomous agents in the past.
And what's that conflict?
It's the tension between just sheer information overload from the source document and the very acute context bottleneck of our current large language models.
So DeepCode's solution isn't just a small step forward. We should just reveal the main finding right away because it's pretty stunning.
Oh, it really is.
This architecture, it achieves state-of-the-art performance. It surpasses the leading commercial agents, and this is the real headline, it exceeds the performance of PhD-level human experts on the main benchmark.
Let that sink in.
Yeah.
We are talking about an agent that can reproduce a complex machine learning paper with higher fidelity, higher accuracy than the human ML PhDs that were hired to do the very same task.
It just fundamentally changes the conversation about the limits of AI in software engineering. Okay, let's unpack this. Our mission here is to figure out what the structural secrets are, what architectural choices allow DeepCode to achieve a level of implementation quality that is literally beating the best human practitioners in this niche.
Right. And to understand the fix, you really have to understand the systemic breakdown that came before it. You can think of the whole synthesis process paper to code as trying to transmit a huge complex set of instructions through a tiny finite pipe.
And that pipe is the LLM's context window.
Exactly.
So if the scientific paper is, say, the complete blueprint for a chemical plant, the LLM only has a small sticky note to work with at any given time. Most of that detail is just lost.
That's the perfect analogy. And naive strategies, they try to push the entire raw document plus the growing history of the code being written through that pipe. And you get what they call channel saturation, which
Right.
means the massive volume of redundant, narrative information. It just masks the critical constraints, the exact math, the specific hyperparameter settings, and the signal to noise ratio just collapses.
And before DeepCode, the performance of the best agents really reflected that collapse. I mean, we've got the data point right here. Strong models, like Iterative Agent, they only achieved a 43.3% replication score on this benchmark.
Which is barely getting half the job done. And you compare that against the human expert baseline, these are ML PhDs, who average 72.4%. The AI was it was floundering.
And that huge gap that was caused by 4 specific recurring failure modes, all of them stemming from that information conflict.
That's right. 4 main failure points.
So what were they?
Well, the first was specification preservation. The constraints in a scientific paper are just scattered everywhere. An equation is on page 4, a key parameter is buried in a table caption.
A detail is hidden in the introduction.
Exactly. Agents just struggled to map all those scattered pieces faithfully into the code. They missed the critical low-level details because they were hidden in all that noise.
Okay, and the second one, global consistency. That sounds like a classic software problem.
It is, but it's magnified by the limited context. So when the agent generates, say, file A, and then later on it generates file B, it's often forgotten the specific abstraction it used in file A.
And you end up with broken dependencies.
You do. Function names don't match. Import signatures are wrong. The files can't even talk to each other. It's not just a bug, it's a structural failure.
That makes the code incredibly brittle. And the next failure, completion of underspecified designs, that sounds even harder to solve.
It's the difference between theory and practice. Scientific papers, they focus on the algorithmic core. They almost never specify the non-trivial engineering details like, how to set up the data loading pipeline or the exact experimental framework you need.
So previous agents struggle to guess at those implicit necessary choices that a human expert would just instinctively know to add.
They knew the math, but not the boilerplate code you need to actually make the math run.
Got it.
And that leads to the last one. Executable faithfulness. Even when the agent got the theory and most of the structure right, the long process of generation it led to subtle logic bugs, forgotten dependencies, fragile pipelines that just stop the whole repository from running end to end.
And you need a runnable repository,
Yeah.
not just some plausible-looking code snippets.
Exactly.
Okay, so those 4 failures, noise, inconsistency, missing details, and final fragility, that defines the problem set. So DeepCode addresses these by completely restructuring the process. It's about hierarchical information flow management.
Precisely. It's not about just throwing more tokens at the problem. It's about structure. DeepCode orchestrates the whole task into 3 heavily managed phases. And that ensures that at any given moment, the LLM is only dealing with the highest possible signal.
Let's start with phase 1 then. Source compression via blueprint generation. How do they change the nature of that input document?
So the goal here is to transform that massive, unstructured paper into a dense, high-signal implementation blueprint. They start with a technique called hierarchical content segmentation.
So instead of feeding the whole paper in at once.
Right. They parse it structurally using the section headings, methodology, dataset, and so on. This turns the document into these queryable keyword chunk pairs.
That's a huge efficiency gain right there. You're not asking the LLM to read 50 pages. You're just telling it to reference the 2 paragraphs relevant to optimization parameters.
Correct. And to make sure they capture every single detail, they use a multi-agent system for the analysis. You have a concept agent, which is like the high-level architect. It focuses on the big picture, the structure, the component decomposition, the overall roadmap, the why.
And the other agent focuses on the how much and what.
Yes, the algorithm agent. It acts like a meticulous proofreader. Its only job is to extract the low-level fidelity, the verbatim pseudocode, the exact mathematical equations, the full list of hyperparameters.
So that dual approach ensures you get the conceptual coherence, but you also guarantee the technical precision. It just solves that specification preservation failure right up front.
And the output of this whole phase is the implementation blueprint. It's a structured document. It includes the project file hierarchy, a component specification, a stage development plan. They've essentially solved the long context problem before a single line of code is even written.
That is a foundational shift. Okay, so moving into phase 2, code generation powered by CodeMem and CodeRag. The synthesis is iterative, right? They write file by file.
They do, and the challenge here is how do you keep global track of this growing code base without polluting the context window with all that raw code history?
Because if you keep passing in the raw code, you're right back to that channel saturation problem you just solved.
That's right. And the solution is structured indexing using code memory, or CodeMem. So instead of passing the raw code, a separate summarization agent distills every newly written file into this compact, structured memory bank.
And what's in that summary?
It's not just an abstract. It focuses specifically on the core purpose of the file, its public interface, so what classes and functions are exposed, and its dependency edges. What other files does it need, and who will need to import from it?
That's a really fascinating choice. So instead of passing the full text of file A, they pass a metadata description of file A's public face.
Yes.
And that maintains global consistency without the context bloat. That is genuinely different.
The structure is what matters. It provides exactly the high signal information needed for the next step, the interfaces, without all the low entropy noise of the actual implementation details.
Okay, but what about those missing engineering details, the underspecified design?
That's where the second mechanism comes in. Conditional knowledge injection via CodeRag. That's retrieval augmented generation. This mechanism, it addresses hallucination and that lack of implicit engineering knowledge.
How?
DeepCode indexes high-quality external code repositories, real-world proven code, and it adaptively queries this index during synthesis.
So when the agent realizes it needs a standard way to, parse command line arguments, it doesn't try to guess or hallucinate. It pulls in proven implementation patterns from a knowledge base.
Precisely. It's injecting validated external engineering knowledge only when the blueprint or the ongoing code generation calls for it. And the sources called this out as being indispensable, especially for the smaller, more cost-efficient models.
Oh, that's interesting.
Yeah, the ablation study showed that adding CodeRag to a model like Gemini 2.5 Flash gave an astonishing 70% relative gain in performance. It just completely bridged those inherent knowledge gaps.
A 70% gain is a staggering return for one tweak. Okay, finally, phase 3, Automated verification and refinement. This is the QC layer that fixes that final failure point of executable faithfulness.
It is. It's a closed-loop feedback system, and it happens in two robust
What's
stages.
stage one?
Stage one is static analysis and refinement. An analysis agent scans the newly generated repository against the blueprint, and it checks for structural problems. Did we forget a file? Is the code style poor? Then a modification agent applies precise surgical fixes.
And how is it so precise? You mentioned surgical.
It uses an interface inspired by the Language Server Protocol, or LSP. You should think of the LSP as the underlying language that advanced code editors like VS Code use to talk to language intelligence.
Ah, so it allows the agent to make these really precise line-level changes instead of having to regenerate huge blocks of code.
Exactly. It gives the AI the same surgical toolset that modern code editors give to us human programmers.
Okay, so it's fixing the easy stuff first with high precision, but the code still has to run.
And that is stage two, sandbox execution and functional correction. The repository is run in a completely isolated environment. The execution traces the doubt, stater, any error messages, is captured, it's analyzed, and it's treated as the final corrective signal.
So if it throws an error,
That error message is fed right back into the refinement loop, which triggers the LSP-based function to patch the code until you get successful end-to-end execution. This ensures the output isn't just syntactically correct, but functionally faithful.
that robust three-phase architecture sounds less like a general LLM and more like a dedicated bespoke software development machine.
That's a good way to put it.
Let's look at the numbers, because this is where the conversation turns from just engineering novelty to genuine disruption.
Yeah, the results on the Paperbench benchmark really validate this. The architectural gain provides a massive performance leap, far exceeding what you'd get from just scaling up the base model. DeepCode achieved a 73.6% average reproduction score.
Okay, let's put that in context. That's compared to the best previous general LM agent, which was at 43.3%. We're talking about a near doubling of capability just from restructuring the information flow.
And it decisively outperformed the major commercial agents, too. I mean, things like Codex, that hit 39.97%, Cursor at 58.41%, and Claude Code at 58.71%. DeepCode, on that same subset of papers, averaged an incredible 85.4%.
And what's really critical here, I think, is the comparison where DeepCode uses the exact same base model as those commercial agents. The paper shows it still maintains its advantage.
That's the key point. It proves the power isn't just in the underlying model, it's in the sophisticated agentic architecture layered on top.
That's the takeaway on the commercial side. But the headline metric is the human comparison.
Right. On the challenging three-paper subset, the human expert baseline, this is the average of the best 3 attempts by ML PhDs, was 72.4%. DeepCode's average performance was 75.9%.
Let's just pause on that. 75.9%. Does that mean an ML PhD is just bad at implementation? Or is there something about the benchmark that favors the AI?
It really speaks to the efficiency of the structured approach. I mean, a human expert faces the exact same problem. Information overload, cognitive context switching. They have to read the scattered text, hold the state of the code base in their head, manually search for boilerplate.
All things the AI automates.
Exactly. DeepCode systematically eliminates those friction points through CodeMem, CodeRag, and the blueprint. The system produces production-grade implementations that officially exceed strong human practitioners because the AI just has a better workflow for handling massive documentation.
And the studies confirmed that every single part of this workflow was necessary. Right?
Absolutely. The ablation studies were clear. Removing CodeMem saw scores just plummet. In some tasks, performance fell from 0.70 all the way down to 0.33,
Wow.
which demonstrates just how essential that structured indexing is. And the final layer, automated verification, consistently provided final gains of about 3.7 to 6.5%.
That might sound small, that 3 to 6%, but that's the difference between a broken repository and a runnable one.
It is the difference between failure and success. That stage fixed those small but consequential issues, the dependency typos, the argument errors, that turn a nearly correct implementation into a 100% faithful, runnable replication.
So DeepCode has undeniably validated that the future here lies in this hierarchical information flow management. But the paper itself, it identifies critical remaining challenges. What stands out as the next frontier for these agents?
The first major challenge is definitely computational efficiency. DeepCode's performance relies heavily on calling these massive, very high-cost LLMs. The future is probably in hybrid architectures.
What do you mean by hybrid?
Using the large models only for high-level reasoning and planning, like generating the blueprint and then delegating the routine, less complex implementation tasks to smaller, much more cost-efficient models.
Splitting the mental load across specialized models. That makes a lot of economic sense.
It does. The second frontier is moving from episodic to evolving agents. Current agents, they reset after each project. They don't retain any long-term
They
knowledge.
don't learn from experience.
No. Future agents need post-task reflection to condense execution traces into reusable skills or heuristics. This avoids context bloat in long-term memory, while still letting them accumulate expertise, much like a human engineer learns from their mistakes and successes.
Learning from the past and structuring that knowledge efficiently so the agent actually gets smarter over time.
And finally, there's dynamic planning and adaptability. DeepCode, like most current systems, uses a very linear plan-then-code workflow. You create the blueprint, you follow the blueprint.
But real-world engineering is never that clean.
Never. It requires dynamic bidirectional planning. The future needs execution insights, like an unforeseen constraint you discover during testing, to feedback directly and update the high-level blueprint. That stops the agent from being blindly constrained by a stale plan.
So the core takeaway for you, the listener, is this. The decisive path to robust, autonomous software systems isn't paved with ever larger context windows or eternally bigger models. It is about principled, hierarchical information orchestration. It's about transforming chaotic data into a dense, high-signal blueprint and managing the system's state efficiently throughout the entire project. DeepCode proved that's what it takes to beat a human expert.
Right, and DeepCode focused on reproducing these complex scientific artifacts. So this raises a really important question we want to leave you with. If this rigorous, expert-beating framework can synthesize a complex research paper into a production-grade codebase, what does this breakthrough in high-fidelity synthesis mean for the daily, often repetitive tasks of general corporate software development? And what does it mean for the role of the human engineer in the next 5 years?